Hello, we are Group 7, and this is the proposal for a project called Partial Retinal Image Reconstruction with VAEs. The goal of the project is to use autoencoders to reconstruct full retinal nerve images. Here on the right, we have a retinal nerve volumetric scan. It is composed of slices called B scans that can be seen on the left. We will use compressively sensed B scans with some missing information and recover an estimate reconstruction of the full image using autoencoders. The input is a B-scan with a compressed sampling mask applied to it. It can be seen on the left. A significant amount of information has been set to zero by the mask. The ground truth is a full, unmodified B-scan coming from an optical coherence tomography machine, as can be seen on the right. After an extensive survey of the available OCT retinal nerve datasets, we narrowed our choices down to the following two. Both datasets scanned the retinal nerve in an area of 6 by 6 millimeters, but Harvard Glaucoma Furnace has over 3,000 scans, while Octa 500 has only retinal scans for 300 patients. The trade-off is that Octa 500 offers a much higher scan resolution, as can be seen on the right when comparing with the sample on the left. Furthermore, both datasets offer label data that could be used as site information if it is needed.
So for our baseline, we're starting with a VAE and the reason is straightforward. It's a basic generative model, so it's a sensible first step for reconstruction and for learning a compact latent representation. We're aware that a standard VAE might not be optimal, but since there's limited prior work in our exact setting, using it as a baseline and proof of concept makes sense. From our literature review, we didn't find any attempts to use autoencoders to reconstruct compressively sensed OCT scans, but we did find at least one paper that uses an autoencoder for data reconstruction in another domain, which supports the general feasibility of this approach. So for proposed architectures, it's basically a VAE and two variants. The input is a compressively sensed image X, and for the conditional VAE and VQVAE, we also fit the sampling mask. The encoder is a stack of convolutional and pooling layers that compresses the input into a latent representation, and then in the latent space, the VAE and conditional VAE use a Gaussian distribution, while the VQVAE uses a discrete code book. Then the decoder is a chain of transpose or inverse convolutions to map back to the image space, and the output is x hat, an approximate reconstruction of the ground truth. Expected results. For any of the three models, performance should improve as we increase the latent space size. We also expect the vanilla VAE to be the baseline, so it is going to be the lowest performer overall. Then the other two models should give a noticeable boost. The CVAE gets extra information from the sampling mask, so it's gonna better infer what content is missing. And the VQVAE uses a discrete latent space, which we expect to produce sharper reconstructions. For evaluation metrics, we'll report MSE as the basic error metric as it is commonly used, PSNR to quantify reconstruction quality, and SSIM as a perceptual similarity measure between the reconstructed image and the ground truth.
Now we look at our milestones, timeline, and individual/group responsibilities. Our first week is focused on dataset gathering and exploration. We will conduct comparisons and make a decision. For week 2, we focus on the pre-processing of the data. Raniero will lead and divide the volumes into smaller chunks, perform some data augmentation, and finally develop a custom data loader for PyTorch. Week 3 and 4 will be the initial implementation of our models. I will work on a vanilla VAE, Sama will work on his CVAE model, and Raniero works on the VQVAE model. In week 5, we all plan to conduct experimentation and model refinements. Each member will share the results they obtained in the previous weeks. Feedback and improvement suggestions will be shared among the group, and we'll try to extract as much performance as possible with our models. Finally, in week 6, we share the final results and we'll begin writing our report. We will be using two primary methods of collaboration for our data and code. Data will be uploaded to Kaggle, and all team members will have access. Code will be hosted on GitHub and organized appropriately. We'll have separate repositories for categories of code. All group members will have access to the entire code base. And Microsoft Teams will be our primary communication channel. And that brings us to the end. Thank you.